Okay, so let's continue. Now we discuss the number of divisors. Now we talk about the sum of divisors. The sum of divisors. That's the content of section 3.4. Sum of positive divisors as usual. Positive divisors function. And as usual, we start with the definition, the word notation, and this is our notation for the sum of divisors. Sigma of n is the sum of positive divisors of n. Is sum of positive divisors, all positive divisors. So the sum of all positive divisors of n. As before, okay, first of all, let's see an example. Sigma of 6, or sigma of 6. This time, it's not enough to know the number of divisors. I need to know each one. I need to know what are the divisors, add them up, and see what I get. So it's 1 plus 2 plus 3 plus 6, and it's 12. So sigma of 6 is 12. If I have a prime number, sigma of 41, it has two divisors only. The number itself, the prime number, and 1. So it's 1 plus 41. It's very easy. This function is also multiplicative. And just like the other two before, it's not completely multiplicative. So let's write it. It's, I guess, theorem 3.9, if I'm not wrong, in the textbook. The function sigma of n is multiplicative. And it's not completely multiplicative. We'll see an example in a moment. So let's see a few examples first. Sigma of 4. Sum of all divisors of 4. 1 plus 2 plus 4 is 7. Sigma of 25. When the number is a power of a prime, it's easy to see the divisors are just powers of 5 themselves. So 1, 5, and 5 squared in this case. So it's 1 plus 5 plus 5 squared, or 25. And this is 31. Sigma of 100. Now let's see. We saw earlier that there are exactly 9 divisors, 9 positive divisors of 100. Now we need to add them. Add them up and see what the sum is. So 1 plus 2 plus 4 plus, let's see, 5, 10, 20, 25, 50, and 100. So this equals, let's see, 150, 175, 195, 205, 210, 214, 16, 17, 217. In the case of the sigma function, so the sum of divisors, it may be useful sometimes to use the to appeal to this property, multiplicativity property, because we can write sigma of 100, so sigma of, and write 100 as a product, 4 times 25, using the theorem that this function is multiplicative. This is sigma of 4 times sigma of 25. And they were computed before. Sigma of 4 is 7. Sigma of 25 is 31. 7 times 31 is 217. 7 times 1 is 7. 7 times 3, 21. So it is equal to the 2017 we obtained, so to speak, the hard way, by listing divisors. Now, next order of business. Let's see that this function is not completely multiplicative, which will tell us to be careful when we use this property. I need the two numbers to be relatively prime. If I try, for instance, sigma of 10, just by definition, divisors are 1, 2, 5, and 10. The divisors of 10. So this is 10, 15, 17, 18. But I cannot claim, and it's simply not true, that sigma of 100 is equal to sigma of 10 times sigma of 10. In fact, this is just computed, and it's 18. This is another 18. This one, we computed in two different ways, and it's 217. 18 times 18 is not equal to 217. 18 times 18 is an even number. This is an odd number. 18 times 18, what's 18 times 18? 324? Yeah. 324. They're not equal. So let's write that they're not equal. So we keep this in mind. For every single arithmetic function we discussed so far, Euler functions, number of divisors, sum of divisors, we can use this property. Sigma of a number is equal to the product, but the two numbers need to be relatively prime. However, what we should really do if we have a problem, if we have an exam, things like this, to go directly for the main theorem that tells us, gives us a formula. Like in the case of the number of divisors, it was a simple enough formula, but that was it. It tells us how to compute. This is more complicated, but let's write it anyway. To write it as a theorem, and I guess it's of 3.11 in our textbook. Again, we take n. We use the same prime factor, the same notation for prime factorization. And it's p1 to the a1 times p2 to the a2, and so on. P, doesn't matter how many we have, say r different primes to the a sub r. And again, with P1, P2, PR, distinct prime numbers. And again, A1, A2, AR, positive integers. I was going to say non-negative integers most likely, that's what they're doing, but non-negative integers. But you just don't need it. Non-negative meaning also you can take a 0, but doesn't affect anything. Okay. Non-negative integers. Sigma of n. Once, the fact that the screen is still, yeah. Okay. So sigma of n, and it's complicated indeed. I cannot make something simple if it is complicated by its nature, but not difficult to remember. I take the powers of P1 up to that, and I add all these numbers, starting with 1. 1 plus P1 plus P1 squared, and so on, up to the largest power that I see here, P1 to the A1, times exactly the same expression for P2. 1 plus P2 plus, and so on. P2 up to that exponent, A2. And so on. I multiply up to the last one. 1 plus PR plus PR to the AR. Now, so this is the formula for the sum of divisors. And in practice, I would apply it like this. Of course, no question will appear on a, let's say, homework. I don't know about homework, but certainly no question on the exam where we have numbers like those that we had before. 30 to the 40. Anything, any question about sigma? No. It's going to involve small numbers. Sigma of 100, sigma of 101, sigma of 90, sigma of small numbers. Right. And those we can compute in various ways. By definition, it's a sum of divisors using this property, multiplicativity, or directly by using the formula, which is tempting to use if you want to compute. Because it goes like this. First of all, before I write anything, let's see what I can erase. I rewrite, or I compute again those numbers, this time by using the formula. So to get familiar with the formula. Sigma of 4. I keep in mind that 4 is 2 squared. So I have a single prime, not several factors, a single one, P1. P1 is 2, and the exponent that appears in number A1 is still 2. So I just go with 1 plus 2 squared plus, I stop there because it's 2 squared is the largest exponent, and it's 7. But if I want to compute, say, sigma of 100, question mark, and if I don't have already these two numbers computed, sigma of 4 and sigma of 25, I just proceed directly with this number, like this. So I don't use, I don't necessarily use the, and in the particular case of 100, I don't want to use definition. I don't want to write all these numbers. I want to use this formula. So it goes like this. First I compute, all right, the prime factorization of the number is 2 squared times 5 squared. So I apply formula. Sigma of 100, I take the first prime, it's 2, 1 plus the prime squared, cubed, and so on up to the largest power, it's 2 squared. That's it. 1 plus 5 squared, stop right there, because I have a 5 squared. It's very easy. Then I see what I get. 1 plus 2 squared is 7. 1 plus 5 squared is 31. And the product is 217. So that's all. Let me just compute 2 more, 3 more, and that's that. Wait. I'm going to, no, I don't want to erase the actual formula for the moment. Well, let's compute as some number with lots and lots of divisors and a large sum. Say, what is sigma of 60? Because I don't want to write them down, but I look at the prime factorization. 60 is, it's 2 times 3 times 5. No, I'm wrong. 2 times 3 times 5 is 30. And times another 2. So it was 4 times 15. 4 times this. So 2 squared times this. Good. So then it means the sigma of 60, without writing already, is this. And again, without thinking, immediately applying the theorem. And I don't even need to read this again. I know what it means, or what it says. Take the first prime, 1 plus 2, 2 squared. Done. 1 plus 3 squared. No, there's no 3 squared. Stop right here. 1 plus 5, there's no 5 squared in here. Stop right there, whatever the answer is. 1 plus 2 squared is 7. 1 plus 3 is 4. Then 1 plus 5 is 6. Whatever that is. This is, say, 24 times 7. 24, I'm sure you did it, times 7. 28. 168. Is it? 168. So, I have to read, if I have a problem, I have to read carefully what the problem asks. Maybe a problem asks just the following. What is sigma of 60? And then I need to compute it. This is one way. In this case, it's faster. What is sigma of 61? 62, because this is a prime. So the fastest thing is just to take 1 plus them. All right. So it depends on the situation. But now, suppose we have a problem in which I want to compare two numbers. Which one is larger? So let me there's one more thing I needed to do. But let's see one example and then one general remark about this formula. So if I have to which number is larger? And I said we're going to work with small numbers. Let's see. Is larger. Sigma of 60 or sigma of 201. Well, if I already computed sigma of 60, question mark. I already computed sigma of 60, and found that it's 168. Then, to answer the question, I don't need to compute that. I just need to, you see, I can use the definition for that one. Sigma of 201 is going to be the sum of all the divisors. One of them being 201. Another one being 1. I can see 3 is a divisor because just 2 plus 1 is 3, so it's a multiple of 3. But I don't care. Plus dot, dot, dot. I don't need to compute. I can immediately say that this is larger than 168 because I already have a divisor that's larger. So in some cases, I don't even need to compute. But in any case, we won't have to deal in concrete problems with a very large number, like 30. Certainly not 30 to the 30. Just numbers like this, 100, 200, less than this. I want to make one more remark. There's another formula, but I want to show that it's actually exactly the same thing. Let me write it. In this case, it's sigma of n. So another theorem if you want. Sigma of n is but it has fractions. It has p1 minus 1 in the denominator. It has p2 minus 1 and so on, all the fractions. It's p1 minus 1, and in the numerator is exactly the next power of p. If this is a 1, it's plus 1. So p1 to the 1 plus a1, and then minus 1, times this whole thing, times exactly the same for the others. p2 to this number plus 1, 1 plus a2, and then minus 1 divided by p2 minus 1, and so on. So in some places, some textbooks, some articles, you see it written like this, you see it written like that. We'll see in a moment that it's exactly the same thing. So PR to the 1 plus AR minus 1 over PR minus 1. Now let's see what happens if I use both formulas to compute a number like sigma of 100 that we computed. Even by definition, we found it is 217. If I compute it by this formula, I have 100 is 2 squared times 5 squared. By this formula, it says that sigma of 100 is 1 plus 2 squared times 1 plus 5 squared. We know that this number is equal to 7. This is equal to 31. The product is 217. Suppose I use this new formula. Sigma of 100 is equal. I write it as a fraction. In the denominator, I have the first prime, p1, minus 1. In my case, this is how we factor the number. 100 is 2 squared times 5 squared. The first prime is 2, the next prime is 5. So in these denominators, I'm going to have a 2 minus 1 and a 5 minus 1. That's all. So something over 2 minus 1. Of course, 2 minus 1 is 1. But I'll leave it for the moment this is. And in the exponent, I have the same prime to something that's 1 larger than the exponent that appears in the number. So 2 cubed minus 1. This is one thing. And then it's the same with 5. 1 plus a2. a2 being a1 and a2 being in the prime factorization being 2 and 2. So the next exponent is 5 cubed. So 5 cubed minus 1 over 5 minus 1. I can do it like this. And what I get is not only that the number in the end is the same, but every single factor is the same. So 2 cubed minus 1 over 2 minus 1. 2 cubed minus 1 is 7. 2 minus 1 is 1. 7 over 1 is 7. It gives the same 7. And here it's going to give the same 31. But let's check. 5, I say it's going to be the same 31. Maybe it requires even a bit more work. Because 5 cubed minus 1, what is 5 cubed? But anyway, once we get this, it's 217. So just for us right here, 5 cubed minus 1 is 5 cubed is 125. 125 minus 1 is 124. What I have in the denominator is 5 minus 1. That's 4. When I divide the numerator, this divided by that, is 124 divided by 4 is our 31. Number that we have here, as I said. But let's see that, and this is what happens in general. But let's see why this actually happens. That no matter what number you put here, you always get the same. Although it's not, say, important as far as we are, say, preparation for exams or whatever. But it's good to see, so it's nothing different. You can write this in that form. Let me remove everything. This is a remark that has nothing to do with the sum of divisors function, with the sigma. It's a general identity that we can see. if I take any number x, any power, n plus x to the n minus 1 plus x to the n minus 2 plus plus I don't know how many, x squared plus x plus 1, so all the powers of x from x to the 0, which is 1, up to x to the n, and I multiply this number by x minus 1 equals, I'm going to write the answer right here. But let's compute. I multiply each of these numbers by x, and I get x to the n times an x is x to the n plus 1. There's 1 to the exponent. The next one is x to the n minus 1, but times another x is just an x to the n. The next one is x to the n minus 1. Blah, blah, blah. The last few of them are x squared times x is an x cubed, x times x is an x squared, x times 1 is an x. That's it. And then I have minus 1 times exactly these numbers. Let me write them from the right. Minus 1 times 1 is a minus 1, so I can see where they come. Minus 1 times x is minus x. See, this x will cancel. Minus 1 times x squared is minus x squared. We cancel this. Minus 1 times the next one is minus x cubed. This will cancel. So in other words, everything, or actually almost everything cancels. Let's see what the last one is. Minus 1 times x to the n is minus x to the n. X to the n. So everything cancels up to x to the n, and we are left with just one term here, the first one on this line, and the last one on that line. So this is just x to the n plus 1 and minus 1. X to the n plus 1 and then minus 1. And that's why in all these applications, if you have 1 plus x plus up to some point, x to the n, you can write it as x to the next exponent plus minus 1. So this is equal to this thing divided by x minus 1. Divided by x minus 1. In particular, we saw 1 plus 5 squared was equal to 5 cubed minus 1 over 5 minus 1. And the same for any prime number. And in fact, for any number x, 1 plus x squared is x cubed minus 1 over x minus 1. Because of this cancellation. So I think this is should end our discussion on the sum of divisors. Should we stop this between? Yes. Stop before we talk about the modulus function.